Hi guys, so today we're going to talk about shockwaves. So it's going to be mainly conceptual, but before starting, I just wanted to show you a few things that I forgot to mention previously. First of all, for example, if you have a standing wave, so this is a standing wave here. Let me have an app. If you remember, we talk about sound standing waves in, for example, that could be a flute. And this is the first harmonic. And what you see here, you have a note, and here is an anti-note. What I want to bring your attention to is that here, if you look at the displacement of the particles, so each time there was a sound wave, we talked about that last time. So when you have a sound wave, you have all those particles randomly moving because of the temperature, and then you produce a sound, and all those little particles are going to move about their equilibrium. So there is a displacement, okay? So that displacement can be called the amplitude, okay? But there is also a change in pressure. So we can talk about the amplitude here. It could be the displacement of the molecule here, or the particles. So you see here at the center, at that time here, at that location here, the particles are not moving, so the displacement is zero. At the anti-node here, you see the displacement is maximum, right? And this is the atmospheric pressure. But instead of looking at the displacement, and there is a relationship between them, it's a linear relationship, you see that instead of looking at the displacement, you can look at the pressure. So you see here, this is high pressure, and the maximum pressure when everything is squeezed together, or it's going to be minimum pressure when they all move away from each other. So that will be the pressure relative to the atmospheric pressure. So that means this is larger than the atmospheric pressure. And when the molecules move away from each other, the pressure is less than the atmospheric pressure. At the end here, you have the atmospheric pressure, so the pressure is zero. So you see there is a phase shift, okay, between the displacement and the pressure. So when the pressure is zero, the displacement is maximum. When the displacement is zero, the pressure is maximum. So why I'm mentioning that? It's because when we want to use a sine wave, for example, to represent the sound wave, we don't use the displacement of the particles because it's very hard to measure, but we use the pressure. Okay, so the pressure is going to increase, it's going to decrease, increase, decrease, and so forth and so on. Okay, because in that case, you see, it's easier to measure pressure than it is to measure the displacement of the particles. So when we use a sine wave here to represent the sound wave, you see the amplitude here will be the pressure, so high pressure when everything is squeezed together, and then here will be low pressure. Okay, because last time we talked about the intensity. So the intensity is the energy per unit second per unit per square meter carried by the wave. And you see it's proportional to the amplitude square and proportional to the frequency square. And we discussed that. And in that case, that was the amplitude here is the displacement of the particles. But you can also instead use the pressure, okay, because it will be proportional to each other, except that there is a phase shift of 90 degrees. So it's just a parenthesis. I thought it was interesting to mention. Another thing that I forgot to show you is that you can make you can easily make harmonics sound with sound. This is something you can buy. It's very cheap, and then it's open at both ends, and it's easy to produce the harmonics. So let me show you. I will put the link in the description. So that will be the first harmonic. I don't know if you can hear. And then you can spin faster. That's the second harmonic. And even faster. And then you can get to the third harmonics. And you hear the third. And if you're even faster, you can go to the next overtones. Now, if you take that tube here and instead you do it like this above your head, then you can hear the Doppler effect. So that takes me to the next video, where he did a smart thing. He took like a boombox. I think it's called like a boombox, like a big stereo, and attached that to a string to demonstrate the Doppler effect.
Started. Okay, here I go.
Low frequency, high frequency, low frequency, high frequency. You see, it's a very nice demonstration. I will share it with you. Okay. So let's talk about shock waves. So I still have that nice demonstration here. So we talk about the Doppler effect. So in that case, this is the source, this is the observer, and they are not moving relative to each other. Or I can have the observer moving. So you have more waves, more wavefront hitting the observer per unit second. So the frequency is higher. And then there you see the frequency will be lower, so lower pitch. Or you can have the source moving toward the observer, so increased frequency, more wave front hitting, and low frequency. Or you can have both of them moving. So there is also an equation for that. So they are both moving. So of course, higher pitch past the source. So this is the source here, lower pitch. And then you can have the case when the source is going at the speed of sound or faster than the speed of sound. So that's when you have a shock wave. Okay, so here it's moving. We see that the source is moving faster than the speed of sound. So all those wavefronts tend to pile up. But as long as that this cone here is not sweeping over the observer, no sound can be heard. Okay, so here no sound can be heard. Sound can be heard behind, or here if you are sitting here, it's about to be heard. Otherwise, no sound can be heard. Then it's arriving, and boom, that will be perceived as a sonic boom. Why? Because remember, we add the intensity, right? So all those amplitudes here, all those wavefronts gonna reinforce each other. Okay, so they're gonna be piling up on top of each other. Okay, so it's gonna translate that as a very loud noise. So that will be a sonic boom. And that happens only when that front here is sweeping across that observer. Then there is no more boom. sonic boom and you are hearing a lower frequency. And you see that I don't know if I can go back, but you see it makes a cone. See, you have the cone here. And how spread is the cone? How large is the cone? Depends on the speed. There is an equation for that. There is an equation for everything, which is nice. So that will be shockwave. Happens when the speed of source is greater than the speed of the wave. So in that case, that will be the sound wave. So the medium cannot respond fast enough to propagate the wave, and the crest pile up in front of the source. So that will mean a very large amplitude pulse. So that's how a sonic boom is produced. And if you're making wave, and if the boat is moving faster than the speed of the waves that you make in the water, you have a bow wave. Okay. Okay, so that's how it works. I think I have videos, supersonic. So I found a video, I wanted to show you here. So listen carefully, you're gonna hear the sonic boom. So you hear the sonic boom when the airplane reaches the speed of sound and it's going faster than the speed of sound. And you see also weird light effect around it, right? Let's look. You see this light effect also?
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes...
Did you see the cone form even before it reached the speed of sound? So before talking about that, let's look at this slide here. So what you have to understand is that cone here, you see that cone, you're going to have all those crests from the sound wave produced by the airplane piling up. And that's going to be your shock wave, because when it's sweeping over you, of course, the sound will be very loud. However, if it reaches the speed of sound at that time here, if you are located here and the observer is here, you're not going to hear the sonic boom. If you are here, you are not hearing the sonic boom yet. The sonic boom can be heard only when that cone here is sweeping over you. So you see it makes a cone here. So that cone happens, it's made of water that was condensed, so turned from gas to liquid. And it happens because, first of all, we can visualize the shock wave here. So all those crests piling up. Second of all, when it's moving through the air is going to move very fast here and very fast there. So the pressure, when the air is flowing fast, that makes the pressure go down. If the pressure goes down, the temperature will go down. If the temperature will go down, water vapor will turn into a liquid. So that cone is formed as the airplane move. Okay, it's not attached to the airplane. So that weird cloud will stay wherever it is here. The second thing, you can have also very weird visual effect, because the density of air here, it's going to drop. And if the density of air drops, then light can be refracted. But if you want to know more about that, you can watch the video till the end. It's a very nice video.
You can almost see it. Going close to that speed through air can cause some...
Okay. So the main thing to understand that you can have conceptual question about that. You're not going to hear the sonic boom if you are located here or located there. The sonic boom can be heard only when that cone here is sweeping over you. So we can compute that angle here. It's given by the equation. So everything, math has an equation for everything. It's the ratio between the speed of sound and the speed of plane. And we suppose that the airplane is moving faster than the speed of sound. So that means that ratio will be smaller than 1. So example, if you take 1.5 Mach, so the airplane is moving at 1.5 the speed of light. No, that's not what I want. I want this. So it will be 1 over 1.5, okay? And then you take the sign, so go second sign, the answer, and you get a cone of 41 degrees. So that's going to be 41 degrees. If it's moving faster, so for example, if the airplane is twice the speed of sound, the spawn, the clone, sorry. The cone is going to decrease, right? I mean, the angle is going to decrease. And here I have a link, and I will put the link in the description where, okay, so that's just an application, and I will put the link in the description. So you have a picture here, nice slide in 3 dimensions. If you are standing again here, that cone is not sweeping over you, so there will be no sonic boom. Only the people located here will hear the sonic boom. The one behind will not hear the sonic boom. So you can have a shockwave also, not only with sound, but with water. If a boat is moving faster than the speed of the waves in water, the water wave, you have what it's called a bow wave, right? So you see all the crest here. It's nice because it's even easier to visualize the piling up of the crest here, or throw, the wavefront. You can have also shockwave in space. So for example, if you have a supernova, and a supernova is when a star is exploding in space, and in that case, you have gas all around, and there will be a shock wave. There will be a wave and a shock wave moving through that gas. And that's actually very important because it's like a kick, and that shock wave could kick around in space, promoting new stars to be born. That can cause new stars to be born. So let's see if I have just a picture here, not a picture, a video. That's a supernova shockwave. Beautiful. You see the wave front here, except it's in a 3 dimension. So that's where all the wave fronts are piling up. So just beautiful. So that was for shockwave. Now I want to go back to the Doppler effect, because you can have also Doppler effect for light. And it's important if you are studying, for example, astronomy or astrophysics. So this is light. Okay, you have invisible light and visible light. This is low wavelength, high frequency, and this is low wavelength and large wavelength and low frequency. So everything here can be dangerous. Everything here is safer. Okay. And light move at the speed of light in vacuum, which is 186,000 miles per second. So if you have a source of light, and of course it has to be really fast to see the effect. So you can see that with galaxies, for example, but let's say you have a source of light, so it's moving towards you. You see how the wavelength decreases and the frequency increases. So it means the source is going to be blue shifted. Okay. Because this is red and this is blue. So this is for low wavelength, small wavelength, large wavelength, high frequency, low frequency. So if you start from a green light, let's see the source here, just for the sake of the example, let's say you have a green light, okay, and it's moving really fast. If it's moving really fast towards you, the source will appear blue to the observer. So of course the source didn't change color, the source is still green, but for an observer, if it's moving toward the observer, it's going to be blue shifted. It will appear blue. If it's moving away from the observer, it will appear red. Okay, so that's the idea. Imagine you have a green source and it's moving in this direction. So for that person, green will appear blue, and for that person, green will appear red. So we call that redshift, and we call that blue shifted. So this is just, it's more complicated than that, but just for you to get the idea, let's say you have a star and it's a green-yellow star. If the star is moving away from us and the speed are huge, so you can actually measure the redshift. So it's going to appear red. If the star is moving towards you, it's going to be blue. So blue shifted, red shifted. It doesn't have to be stars. It could be also galaxies moving toward us. So it's blue shifted, away from us. So it's red shifted. So of course, it's not really the color that we scientists are looking at. It's the spectrum. So if you look at a star, or if you look at a galaxy, for example, through a prism, you're going to see the rainbow, right? Like you look at the sun, you're going to see a rainbow. And of course, you have the visible light, but here you have other light like infrared, and beyond that you have UV. And superimposed to that rainbow, you have those black lines, okay? And those black lines, so this is called a spectrum. Those black lines is just blueprint that will tell you is the chemical composition. So maybe these two lines means there is hydrogen, these lines means there is helium, whatever. The point is that if you are looking for a prism at any source of light, you're going to see those black lines, okay? It's called a spectrum. And so if the source of light is moving toward you, so then you're going to see those lines being shifted to the blue. If the source of light, and that could be a galaxy, a star, or even maybe a planet, if it's reflecting light, then those black lines will be red shifted. Okay? So these are called spectral lines. So you have many applications in astronomy with that Doppler effect for light. So for example, in the 1920s, Edwin Hubble and others noticed that the spectra from galaxies beyond our local group, they were all redshifted. And farther away was the galaxy, more redshifted it was. So that means all the galaxies, including ours, are moving away from each other, which means that the universe was expanding. But that's not the only application. Like, it's very hard to detect an exoplanet directly. So you cannot, it's very hard to see it with a telescope, for example, because it's so small and doesn't emit enough light. However, if it's orbiting a star, what's going to happen? The star is tugging on it. So that's why it has to orbit the star. But in reaction, the planet is also tugging on the star. So the star is going to wobble, right? This one is moving away, that one is moving toward, because of conservation of momentum. So if it's moving toward us, it's going to be blue shifted. Away from us, it's going to be red shifted. So from that, we can find the speed of the planet, the speed of the sun, or the star, the distance between them. We have to use other physics law, including the conservation of momentum, the law of gravitational, the universal law of gravity, but we use the Doppler shift here to find the mass of a star and the mass of the planet. Or it could be also a binary system, so you can have a small star and a big star here, and you can find the masses of the stars this way. So very simple example here. We can use that equation that works if the speed is much smaller than the speed of light. Okay, so if there is a shift, so for example, this is the spectrum that you expect in a line in a lab, and this is the spectrum that you observe, actually observe. You can find that shift here in wavelength. So the x-axis is the wavelength. Okay, so there's a shift in wavelength. By finding that shift, then you can find the speed of the source. So let's do quickly the problem, and it will make more sense. It's a very easy problem. So in the lab, you have one line. Maybe it's a hydrogen lab. I forgot. I don't know. So this is the wavelength. Okay, so it's at rest in the lab. Okay, so it's a wavelength somewhere here. It's supposed to be there, for example, unshifted. And now we observe it's being shifted. So it's 4,000 angstrom, and it's observed to be 3,999 angstrom. So it's being shifted, right? It's smaller, so that means it's blue shifted. So it's moving toward, right? So all you have to do, you forget about the sign, moving toward. And all you have to do is to apply that equation. So it's going to be 4,000 minus 999 here over 4,000. That's going to be the speed of the source over the speed of light. And the speed of light is 3 times 10 to the 8. So you can pause the video and see what you get. I got, okay, so that's the relative shift, 0.00025. So that will be the relative, the speed of the source relative to the speed of light. So 0.0, that means that the speed of the source is about 0.025% of the speed of light. So much smaller, but still large, because if you do the computation, so if you multiply that number by c, so this is equals to v times c, so you can find v, you find 75,000 meters per second. Okay, so you get the idea. So I forgot to mention that, because I don't want to start lecturing about astronomy and atomic spectrum, but these here the x-axis is wavelength. So you are missing this wavelength here, this blue wavelength is missing, this red wavelength is missing. That's, it's the blueprint for some elements that are, here. So that could be, for example, hydrogen. That means you have hydrogen. This one means maybe you have calcium. Just giving you the idea. It's just the idea. That's the idea. So, for example, here's another example. Of course, you have to go really, 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 really fast to go toward the yellow light and to see green light. So you can explain to the office officer that because of the Doppler effect of light, you are not guilty to to burn the light, because if you are going really fast, yellow will appear green. So I don't know if that can work as an argument, but you can do the computation, and I got 0.068 V over C. So that's already much more, because that means it's going to be 6.8% the speed of light, if you were to have that argument here. So that speed will be, so if you compute the speed, it's going to be 2 times 10 to the 7 meter per second. Of course, it's very fast. Miles per second, okay. Will be very fast. Cannot be, right? It's not possible. Okay. I'm going to put all the links. I might do another video, last video, in the series. But what I meant earlier, to make sure you understand, is that, for example, if there is hydrogen in a gas around a star, for example, you expect to have those black lines superimposed to the rainbow. If you have calcium, you expect those black lines to be superimposed here. Okay? So by looking at those spectra, you can tell the chemical composition of gas surrounding a star. So any source of light, if you look at that light through a prism, then you're going to see those black lines. So each black line will match with a wavelength. I hope it was clear. You see hydrogen. So for example, hydrogen, you expect a line in the blue, a line in the red. Helium will be a yellow here, and so forth and so on. You have also lines over here and lines over there, but they are not visible. Okay, so one more video about optic wave, and that will be it.